Hello dear friends, make yourselves comfortable. In this video, I will tell you how the comet, or rather the 3I Atlas spacecraft, surprised us again. Believe me, you have something to hear. So please like this video and subscribe, as I try to share the most relevant and expert information with you. Let's start with... Imagine a cold November dawn. The air is sharp enough to see your breath. A telescope points toward the eastern horizon, where the sky deepens from black to indigo. Stars are still visible, but the sun is close behind them. And there, just 16 degrees from where daylight will soon rise, a faint blur of light emerges, a signal that has travelled for billions of years. The interstellar comet 3I Atlas has returned. On October 31, 2025, while most of the world celebrated Halloween, astronomer Qichang Zhang was capturing something far more extraordinary: the first confirmed image of 3I Atlas after its disappearance behind the Sun. For almost a month, the comet had been invisible, lost in the Sun's glare. Using the 4.3-meter Discovery telescope at Lowell Observatory in Arizona, Zhang recorded the comet's faint light just above the brightening horizon, a delicate, high-risk observation that demanded precision and courage. At that moment, the comet was only 16 degrees from the Sun. To imagine that distance, hold your fist at arm's length against the sky. That's about 10 degrees. The telescope was pointed less than 2 fist widths away from the blinding light of our star. Morning twilight had already begun to wash the sky with blue. A slight miscalculation could have destroyed sensitive optics or rendered the image useless. But the risk paid off. 2 days later, on November 2nd, Yang photographed the comet again, this time with a 1V52 mm 6-inch Ritchie-Chrétien reflector, a small telescope comparable to what many dedicated amateurs own. It was a modest setup by professional standards, but it worked. 3I Atlas appeared clearly, a dim, compact smudge moving slowly among background stars. This moment changed everything. For the first time since the comet's disappearance in late September, ordinary observers with accessible equipment could view an object from another star system. No need for Hubble or JWST, just clear skies, a low eastern horizon, and a well-aligned amateur telescope. Zhang cautioned that the comet would not look spectacular, just a faint patch of light, but the significance was profound. Anyone, anywhere, could now witness an interstellar traveller. What had been the domain of scientists suddenly became a shared experience for anyone willing to wake up before sunrise and aim their optics toward Virgo. At perihelion on October 29th, the comet reached its closest point to the Sun about 203 million kilometers away, or 1.36 astronomical units. This is when comets are most active. Solar radiation heats the nucleus, causing frozen gases to sublimate directly into vapor, forming a glowing coma and tail. Normally, that's when comets shine brightest. But from Earth, 3I Atlas was positioned on the far side of the Sun, completely hidden. Ground-based telescopes could observe nothing. Space-based observatories filled the gap. Instruments like STEREO, Solar Terrestrial Relations Observatory, SOHO, Solar and Heliospheric Observatory, and even the GOES-19 weather satellite continued watching. Built to monitor solar activity, these spacecraft inadvertently became our only eyes on the comet during its critical weeks near the Sun. The data they captured turned out to be both surprising and controversial, but that part of the story unfolds later. By early November, 3I Atlas began rising higher in the morning sky each day. Within a week, it had moved 25 to 30 degrees away from the Sun enough for larger telescopes around the world to begin safe observations. This widening angle meant darker skies and longer viewing windows each morning. For northern observers, the comet was climbing steadily northward, easier to see each day. So what were astronomers actually seeing? Through the eyepiece, 3I Atlas appeared as a compact, slightly fuzzy white dot. Its coma, the diffuse halo of gas and dust, surrounded a bright core. Under longer exposures, faint hints of a tail appeared, though nothing like the dramatic displays of comets Hale-Bopp or Leonard. Its brightness hovered around magnitude 9 to 10, well beyond naked eye visibility, but within easy reach of small telescopes and binoculars. For context, the dimmest stars visible without aid are around magnitude 6. Each step of 1 magnitude equals roughly a 2.5x change in brightness. So 3I Atlas was about 16 times fainter than the human eye can detect unaided. Observation conditions improved rapidly. On November 9th, for observers at 40 degrees latitude, the level of Denver or Philadelphia, the comet reached an altitude of 10 degrees just before dawn. The waning gibbous moon added some glare, but by November 16th, the moon had shrunk to a thin crescent only 4 Degaran south of the comet. From mid-November through early December, lunar interference would be minimal, providing ideal dark skies as 3I Atlas moved through Virgo. Several beautiful alignments followed. On November 18th and 19th, the comet passed 1.5 Degreeland south of Gamma Virginis, Porrima, a bright reference star perfect for locating it. On November 2010th, it brushed close to the 13th magnitude galaxy, NGC 4454, a striking opportunity for astrophotographers to frame a comet from another star system against a background galaxy of hundreds of billions of stars. Zhang's observations hinted that the comet might still be brightening even after perihelion. Unusual, but not unheard of. Some comets continue to increase in brightness for days or weeks as sunlight penetrates deeper into the nucleus, releasing new material. Whether 3I Atlas would follow that pattern remained uncertain, but the prospect drew astronomers worldwide to their instruments. The Lowell Discovery Telescope's role was vital. Few major observatories can safely point so close to the horizon, where turbulence, light pollution, and physical constraints of domes make observations difficult. Lowell's 2,260-meter elevation in northern Arizona, combined with its flexible mount design, allowed Zhang to exploit a narrow viewing window just minutes long when the comet was visible, but the sun still below the horizon. Waiting a few days longer would have meant losing the chance. Starting earlier could have endangered the equipment. Such work depends on timing, judgment, and calm under pressure. Now that 3I Atlas has re-emerged, observatories worldwide have added it to their schedules. Spectrographs are analysing its gases. Photometric systems are tracking brightness variations. Radio telescopes are listening for emissions. Each data point helps answer fundamental questions. What is this nucleus made of? How does its chemistry compare to comets born in our own system? What can it tell us about the molecular cloud where it formed billions of years ago? Even spacecraft beyond Earth's orbit are involved. The European Space Agency's JUICE, Jupiter Icy Moons Explorer, is set to observe the comet in November with multiple instruments. Though farther away than the Mars orbiters were during the October flyby, JUICE will see 3I Atlas just after perihelion, when it should be most active. Data won't arrive until February 2026, but it promises a fresh perspective. There is something quietly moving about this return. For nearly a month, the comet was hidden from all view, changed perhaps by its encounter with the sun's heat. Now it's receding along a hyperbolic trajectory, a path that will carry it out of the solar system forever. Unlike Halley's Comet, it won't return in decades or millennia. This is its only visit. Every observation counts, because once it's gone for good. Across the world, amateur astronomers set their alarms for the early hours. They step into the cold, set up telescopes, and trace the comet's faint glow above the horizon. Some succeed, others lose the view to clouds or city lights. But all of them are witnessing photons that began their journey from another star system, light that crossed interstellar space, filtered through our atmosphere, and landed on their sensors. Each image carries a message from elsewhere in the galaxy, waiting to be understood. Something unexpected happened in the days that followed. The comet that had quietly reappeared in the dawn sky became a global story, an unlikely mix of science, media, and modern culture. It started on October 31st, 2025, when a single post on social media set off a chain reaction. Kim Kardashian, one of the most followed people on the planet, wrote on X, formerly Twitter, "Wait, what's the deal with 3I Atlas?" The post was casual, but it reached hundreds of millions of people within hours. NASA's acting administrator, Shah Duffy, replied publicly, "This is the third interstellar comet observed passing through our solar system. No aliens, no threat to Earth." That exchange marked a shift. A faint comet had just crossed into mainstream awareness. The timing wasn't random. For weeks, online speculation had been building. Conspiracy-themed channels on YouTube were producing videos with titles like "Is 3I Atlas an alien probe?" and "NASA's secret comet cover-up." On Reddit, threads filled with speculation and doctored images. Then came something more dangerous: AI-generated deepfakes of well-known scientists. One viral clip appeared to show physicist Brian Cox discussing non-natural origins for the comet. The video looked real, complete with synthetic voice and facial motion. Cox responded quickly, warning that the problem went far beyond astronomy. "It doesn't matter if this time it's nonsense about a comet," he wrote. "What happens when the same tools are used for politics or medicine?" YouTube eventually removed the fake accounts, but not before millions had watched them. The idea that 3I Atlas might be something else had escaped the niche corners of the internet. Then another familiar name entered the story: Avi Loeb, the Harvard astrophysicist known for provocative ideas about interstellar objects. On October 30th, Loeb appeared on the Joe Rogan Experience, one of the most widely heard podcasts in the world. The conversation turned to 3I Atlas, and Loeb didn't hold back. He criticized NASA for delaying the release of images taken by the HiRISE camera aboard the Mars Reconnaissance Orbiter on October 2nd and 3. Those images, captured when the comet passed 30 million kilometers from Mars, achieved a spatial resolution of about 30 km per pixel, roughly 3 times sharper than the best public Hubble images. They offered a unique side-on perspective of the coma and outflowing material. Yet 4 weeks later, the images still hadn't been released. When Rogan asked if NASA was hiding something, Loeb dismissed the alien theory, but took aim at bureaucracy. "It's probably not extraterrestrial intelligence, just terrestrial stupidity. Science shouldn't be held hostage to government shutdowns." He was referring to the US government shutdown that had begun on October 1st, halting data processing at several NASA centers. Loeb argued that critical time-sensitive data was being wasted. The podcast reached millions of listeners in a single day. Rogan urged Loeb to contact Administrator Duffy directly. Loeb did, and also reached out to Congresswoman Anna Paulina Luna, a Republican from Florida, known for her interest in UFO hearings and government transparency. On October 31st, the same day as Kardashian's tweet, Luna sent a formal letter to NASA. It demanded immediate release of the high-rise images, emphasizing their superior resolution, 30 km per pixel, 3 times better than Hubble's best images of 3I Atlas, she wrote. She also requested any supplementary data from Mars missions that may have detected unusual activity near Mars during the flyby and open phase that fueled speculation. Luna went further, urging NASA to use the Juno spacecraft orbiting Jupiter to observe the comet during its future March 2026 flyby. On November 3rd, she posted the letter publicly on X, tagging Shah Duffy. "Please see below. We'd like to see images of 3I Atlas." NASA's response was measured. Duffy reiterated the agency's official stance. 3I Atlas is the third known interstellar comet. It shows no signs of being artificial and poses no threat to Earth. Lead scientist Tom Statler added that the comet very strongly resembles natural comets. The controversy might have ended there, but Loeb replied in interviews that NASA's certainty was premature. Declaring the matter settled without releasing all data, he said, is not how science should work. Soon, investigative journalist Christina Gomez uncovered that Luna had actually sent 2 letters. The first, dated July 31st, proposed a $15 million 6-month extension of Juno's mission to intercept the comet in 2026. The second, after NASA failed to respond, was far more confrontational, demanding data already collected. The story drew in others. Elon Musk made cryptic comments on his social media accounts. Tech influencers began fielding comet questions from audiences more accustomed to gadget reviews. What had started as a quiet scientific event became a cultural phenomenon, a collision of politics, celebrity, and cosmic curiosity. Several themes converged: public distrust of institutions, the demand for transparency, and fascination with anything hinting at the extraterrestrial. The deepfake episode exposed how misinformation spreads faster than it can be corrected. YouTube's algorithms promoted the most sensational claims. Calm scientific updates competed with headlines about alien motherships. In that environment, a Harvard professor questioning NASA and a congresswoman demanding data release were irresistible storylines. Scientists found themselves explaining orbital mechanics and spectroscopy to audiences numbering in the hundreds of millions. Reactions inside the scientific community were mixed. Some welcomed the attention. It's rare for astronomy to dominate headlines. Others worried that serious research was being buried under noise. Loeb became the lightning rod. Critics accused him of chasing publicity for his Galileo project, while supporters saw him as a needed contrarian. The truth lay somewhere in between. Whatever Loeb's motives, the uproar forced NASA to engage the public more directly and highlighted how slow data release can hinder collaboration. It also reminded people that interstellar visitors are not just abstract scientific curiosities, they are tangible pieces of other star systems passing through ours. By early November, the high-rise images still hadn't been released, though scientific papers about 3I Atlas continued to appear. The comet itself kept moving through space, untouched by the arguments on Earth. Kim Kardashian's tweet might seem trivial, but it marked a threshold. When someone with that reach asks about a comet, it means astronomy has entered everyday conversation. Whether that's good or bad for science depends on perspective, but it proves something powerful. People still look up. There is something quietly democratic about the night sky. A photon that leaves the comet 3I Atlas does not care whether it strikes the mirror of the Hubble Space Telescope or the lens of a backyard instrument. The physics is the same. The information it carries is identical. By early November 2025, that idea had become real for thousands of amateur astronomers. They could observe an interstellar object themselves. The turning point came when Qichang Jiang published his November 2nd image, taken with a 152mm telescope. Within hours, astronomy forums lit up. Questions appeared everywhere. Can I see it with an 8-inch Schmidt-Cassegrain? What exposure time works best? Is my suburban sky dark enough? Within 48 hours, answers began arriving in the form of images. An observer in Arizona reported a clear detection using a Celestron 8-inch telescope and 20 stacked 30-second exposures. Someone in New Mexico used a 10-inch Dobsonian and made a sketch at the eyepiece, a diffuse circular glow with a faint tail stretching southwest. A photographer in California combined 200 telephoto frames to reveal not only the comet, but also several background galaxies. For once, a scientifically important object was bright enough for ordinary telescopes, yet valuable enough that every image mattered. Most professional observatories can observe a comet only in short scheduled windows. Amateurs with flexible time and worldwide coverage can watch nightly. They become the bridge between professional snapshots, catching sudden brightening events, or structural changes that might otherwise go unnoticed. This global network gives near-continuous monitoring. When dawn ends observations in Europe, night begins in Asia, then crosses the Pacific to the Americas. 3I Atlas rises before sunrise everywhere, creating a natural relay across time zones. One observer finishes, another begins. Technically, the requirements are modest. The comet's brightness of magnitude 9 to 10 makes it visible in binoculars under dark skies barely, but detectable with guidance. A 4-inch telescope shows it as a small fuzzy patch. A 6 to 8-inch scope reveals a defined coma. Instruments 10 inches and larger start hinting at tail structure. Exposures typically range from 30 seconds to 2 minutes, long enough to gather light but short enough to avoid motion blur as the comet drifts among the stars. After imaging, frames are stacked combined to reduce noise and enhance faint detail. Unlike galaxies or nebulae, a comet moves relative to background stars, so stacking must track the comet, not the sky. Specialized software aligns each frame on the comet's nucleus, leaving the stars as streaks while the comet remains sharp. Some astrophotographers turn this into art. A crisp comet centered amid radial star trails, a visual trace of motion through space. Others create time-lapse animations, compressing hours into seconds to show 3I Atlas gliding across the field. Beyond aesthetics, these sequences are valuable demonstrations of orbital mechanics made visible. The amateur community organized rapidly. The 3I Atlas TV account on X became a clearinghouse for images and data. Observers tagged their photos, compared equipment settings, and offered advice. How to prevent dew on optics, how to process faint tails, how to compensate for twilight glare. Instead of competition, there was cooperation, each success helping others achieve the same. For many, This was their first encounter with an interstellar visitor. The first known interstellar object, 1I Oumuamua, discovered in 2017, was far too faint once its nature was confirmed. The second, 2I Borisov, in 2019, reached only magnitude 15, visible only to experienced imagers with large instruments. 3I Atlas, brighter and higher in the sky, was accessible to high school observatories and local astronomy clubs. Educators recognized the opportunity. Schools organized pre-dawn observing sessions. Universities integrated 3I Atlas into undergraduate labs, teaching spectroscopy and photometry with real data. Planetariums hosted viewing events despite the early hours. For northern observers, conditions improved daily. By mid-November, the comet rose about 2 hours before the sun, high enough for comfortable viewing. Cold air provided exceptional transparency, unpleasant for observers, but perfect for astronomy. Southern Hemisphere observers faced tougher odds. The geometry favoured the north, but determined astronomers in Australia and South America caught it low above the horizon before sunrise. Global coverage remained uneven but still valuable. Their data filled in the picture of how the comet evolved as it climbed. Technical debates took on new relevance. Which eyepieces best show low-contrast objects? Which camera sensors are most sensitive to the blue-green emissions of cometary gases? How does a refractor's crisp contrast compare to a reflector's light-gathering power under twilight? Normally, abstract discussions now had a living target. Some advanced amateurs went further, capturing spectra of the comet separating its light into colours to identify chemical signatures. Low-resolution spectra confirmed carbon-based compounds in the coma, matching professional observations. While less precise than data from JWST, these spectra demonstrated that meaningful science can come from modest equipment. Others performed photometry, measuring brightness precisely night after night to track subtle variations. Such monitoring can reveal rotation periods or outgassing surges. Professional instruments offer higher precision, but amateurs provide continuity. Hundreds of measurements across the globe forming a complete light curve. Observers described the experience in simple human terms. One wrote of setting up at 4:30 a.m., hands numb in the cold, watching breath clouds drift through the red beam of a headlamp. When the comet appeared exactly where predicted, they felt, as they put it, a connection across billions of years and impossible distances. Another recounted showing it to a curious neighbour who stared silently and whispered, "We really aren't alone, are we?" Not in the sense of life, but in the sense of shared existence within a galaxy full of worlds. As December approached, anticipation grew. 3I Atlas was climbing higher before dawn, reaching its closest approach to Earth on December 19th, about 270 million kilometers away. If the brightening trend continued, it might even reach magnitude 8, visible in binoculars under dark skies. The moon would be new in mid-December, leaving the mornings dark and clear. For thousands of amateurs worldwide, this was the peak, the moment to record a once-in-a-lifetime visitor before it moved on. The beauty of it was its accessibility. 3I. Atlas wasn't hidden behind restricted data or million-dollar telescopes. It was there for anyone willing to look up. The cosmos, it seemed, still belonged to everyone. While 3I Atlas was hidden behind the sun, something unexpected happened. The comet became brighter, far brighter than any model had predicted. Its increase in luminosity outpaced every known behavior of typical comets. Astronomers studying data from space-based observatories realized they were facing a puzzle with no simple answer. The first clues came from instruments never meant to study comets at all: the Solar Terrestrial Relations Observatory, STEREO, the Solar and Heliospheric Observatory, SOHO, and the GOES-19 weather satellite were designed to monitor solar activity and space weather. Yet as 3i Atlas passed through their fields of view in late September and October, they recorded something remarkable. Researchers Qichang Zhang of Lowell Observatory and Carl Battams of the US Naval Research Laboratory analyzed the data and posted a preliminary paper on the Ahrumshow server. Their findings were striking. 3i Atlas brightened with a rate proportional to the inverse of its distance from the Sun raised to the power of 7.5 plus. 1. For context, most comets follow an exponent between 2 and 4. A value near 7.5 is extraordinary. The paper's wording was cautious, as scientific writing must be, but the implication was clear. The reason for 3i Atlas's rapid brightening remains unclear. That understated line became one of the great mysteries of this interstellar visitor. To understand the anomaly, it helps to recall how comets behave. As they approach the Sun, solar radiation heats their surfaces, causing frozen gases, mainly water, carbon monoxide, and carbon dioxide to sublimate directly from solid to vapor. This process releases dust, forming the glowing coma and tail. Normally, brightness increases smoothly as distance decreases, but 3i Atlas brightened far faster than the standard pattern suggested. Either its composition is fundamentally different, or its physical behavior, perhaps its internal structure, does not resemble that of solar system comets. Zhang and Battams proposed several possible explanations. The first involves velocity. 3i Atlas moves at roughly 137,000 Alcipadums, 220,000 km/h, significantly faster than typical Oort cloud comets, and faster than either of the previous interstellar visitors. Such speed means rapid heating. Energy from sunlight deposits faster than the surface can dissipate it, possibly triggering violent outgassing that changes the usual scaling laws. The second hypothesis concerns composition. 3i Atlas may contain an unusual mixture of volatile ices inherited from a star system unlike our own. If its nucleus holds a higher ratio of carbon dioxide to water, the behavior changes. CO2 sublimates at lower temperatures than water ice. As it vaporizes early, it can cool the surface through evaporative cooling, delaying water sublimation until closer to the Sun. Once solar heating becomes intense enough, the water ice releases suddenly, producing a dramatic surge in brightness. Observations from the James Webb Space Telescope, JWST, in August confirmed this pattern. Webb's near-infrared spectra showed that carbon dioxide dominated the gas output, while water and carbon monoxide appeared in smaller, distinct proportions. The chemical signature indicates that the comet formed in a molecular cloud with elemental ratios different from those of our solar system, perhaps around a star that no longer exists. A third clue came from color measurements. Near perihelion, photometry showed 3i Atlas to be noticeably bluer than the Sun, an unexpected trait. Comet dust usually scatters sunlight toward the red end of the spectrum, and colder surfaces should appear reddish. Blue coloration points to gas emission rather than reflection. Specific molecules, especially ionized carbon monoxide, CO+, emit strongly in the blue region when energized by solar radiation. This suggests that much of the comet's brightness near perihelion came from active gas, not sunlight reflected off dust. Inevitably, Avi Loeb entered the discussion again. In a short commentary, he noted that blue emission could, in principle, be produced by artificial light or heat sources, though he immediately acknowledged that natural ionized gases were a far more likely cause. His point was not to claim an artificial origin, but to argue that anomalous data deserve open investigation rather than dismissal. Among scientists, opinions diverged. Some saw 3I Atlas as evidence that interstellar comets carry distinct chemistries, reflecting different birth environments across the galaxy. Our solar system's comets record the makeup of the cloud that formed the Sun 4.6 billion years ago. 3I Atlas, perhaps 7 to 11 billion years old, offers a chemical sample from another epoch entirely. Others cautioned that the observations might exaggerate the anomaly. Solar coronagraphs like STEREO and SOHO were not optimized for precise comet photometry. Their data contain uncertainties, and known comets already show wide variability in brightness. Perhaps 3I Atlas lies at the extreme end of natural diversity, not outside it. Even so, the numbers were hard to ignore. The paper concluded, without an established physical explanation, post-perihelion behavior remains uncertain. Continued brightening is as plausible as rapid fading. In other words, no one knows what happens next. New observations from ground-based telescopes will decide which scenario holds true. If brightness keeps rising, the case for an unusual mechanism strengthens. If the comet stabilizes or dims, the flare may have been a transient phase driven by specific ices. One promising hypothesis is delayed water ice activation. When CO2 sublimates early, it cools the surface enough to keep water ice frozen longer. Eventually, sunlight overwhelms this cooling effect, triggering a sudden outburst of water vapor. That delayed ignition could explain both the sharp brightening and its timing. Supporting evidence comes from the SPHEREX spacecraft, which in August measured a carbon dioxide plume extending 348,000 kilometers from the nucleus, an enormous halo indicating intense CO2 activity. If that carbon dioxide outflow indeed cooled the comet's surface, it may have kept most of the water ice dormant until perihelion. When the solar heating finally surpassed the cooling, water sublimation began abruptly, releasing large amounts of gas and dust, and with them light. Additional confirmation came from NASA's Neil Gehrels Swift Observatory, which detected hydroxyl, OH, gas around 3I Atlas. Hydroxyl is produced when sunlight breaks apart water molecules, serving as a clear indicator that water was now active in the coma. The key question remains: did water activity increase suddenly near perihelion, or has it been steady all along? Upcoming spectroscopic studies aim to answer that by comparing the relative strengths of water and carbon dioxide emissions over time. If water signatures are rising sharply while CO2 levels fall, the delayed activation model gains weight. If CO2 remains dominant, something else may explain the surge. The brightening mystery also raises questions about mass loss. Avi Loeb calculated that if the increase in luminosity was caused by extreme outgassing, the comet might have lost up to 10% of its total mass at perihelion, an enormous amount. Such mass loss should leave behind a large debris cloud, detectable as a faint, extended halo in coming months. The European Space Agency's JUICE spacecraft, scheduled to observe 3I Atlas in November, could be the first to detect this debris field. Data won't arrive until February 2026 due to transmission delays, but if confirmed, it would reveal how violently the comet reacted to solar heating. Losing 10% of its mass would mean the evaporation of an average 4 centimeter surface layer across the entire nucleus, significant for an object estimated between 440 meters and 5.6 kilometers in diameter. If JUICE and ground-based telescopes find no debris field, it would imply that the brightening was not purely due to standard gas release, pointing toward more complex, possibly structural or compositional causes. This is what makes the investigation so compelling. Science often begins with anomalies data that do not fit the model. The task isn't to confirm expectations, but to understand what the universe is actually doing. Each hypothesis about 3I Atlas generates testable predictions: light curves, spectra, dust morphology, and post-perihelion fading rates. Over the coming months, astronomers will collect the evidence needed to narrow them down. This process is a reminder of how scientific knowledge grows, not through certainty, but through methodical persistence. 3I Atlas has given astronomers something genuinely puzzling to explore, a case where every observation deepens our understanding of comets, interstellar chemistry, and the diversity of materials drifting between stars. In the end, the mystery of the brightening may have a simple explanation, or it may reveal new physics of volatile ices under interstellar conditions. Either way, the comet is teaching us something we didn't know before. December 19th, 2025. That date marks the comet's closest approach to Earth, roughly 269 million kilometers, or 1.8 astronomical units away. It's the last major opportunity to study 3I Atlas before it continues outward toward Jupiter and then beyond the solar system. Every telescope capable of tracking it will be aimed skyward. The build-up begins weeks earlier. Each morning, the comet rises higher in the pre-dawn sky. Its altitude above the horizon increases daily, giving longer, darker observing windows. By early December, 3I Atlas appears several hours before sunrise, bright against a clean background of stars. The new moon on December 1st provides perfect conditions: dark skies, little glare, and a cooperative schedule. For once, nature aligns with human timing. Professional observatories are ready. The Hubble Space Telescope, which captured images of 3I Atlas in July when it was 227 million miles from Earth, will take another series in December. With the comet now closer and still active, Hubble may resolve fine structures in the coma or even reveal the nucleus itself if the dust clears enough. The James Webb Space Telescope, observing in the infrared, will continue spectroscopic monitoring to measure changes in composition. Earlier, Webb data in August detected carbon dioxide, water, and carbon monoxide in the coma. The December spectra will show whether those ratios shift as different ices sublimate, or whether the dominance of carbon dioxide persists. On the ground, telescopes across both hemispheres are dedicating nights to the comet. The Gemini North and South Observatories, the Keck Observatory in Hawaii, and the Very Large Telescope in Chile all plan synchronized campaigns. At Keck, previous spectroscopy revealed an unusual emission line from nickel without a corresponding signal from iron, a ratio Inuyasha rarely seen in comets. Continued monitoring may clarify whether that anomaly persists or was a temporary feature near perihelion. Radio observatories will also be listening. Though comets emit little radio energy themselves, specific molecules in the coma produce millimeter wave emission lines detectable by arrays like ALMA in Chile. Such signals could reveal rare compounds chemicals that condensed in the environment of another star billions of years ago and have remained frozen ever since. For scientists, December isn't just a viewing opportunity, it's a test of hypotheses. If the comet truly lost large amounts of material during perihelion, telescopes should detect a broad debris cloud surrounding the nucleus. Its shape and brightness would reveal how violent the outgassing was. If no debris appears, the earlier brightening must have had another cause, something deeper within the comet's structure or chemistry. Another key question is non-gravitational acceleration. Measurements from NASA's Jet Propulsion Laboratory, led by David Farnocchia, detected a small deviation in the comet's orbit near perihelion, an acceleration consistent with jets of vaporized gas. Precise astrometric tracking in December will confirm whether that effect continues. If the trajectory still deviates beyond what outgassing can explain, something more complex may be influencing its motion. For amateur astronomers, December is the reward after months of pre-dawn sessions. 3I Atlas could reach magnitude 8, faint but visible through binoculars under dark skies. For most, this will be their only chance to see an interstellar object with their own eyes, fleeting and distant, yet unmistakably real. By late December, it will begin to fade again as it recedes from both Earth and the Sun, but the data collected in that window will occupy scientists for years. After its Earth flyby, 3I Atlas heads for Jupiter, passing roughly 53 million kilometers from the giant planet on March 16, 2026. The interaction could be scientifically rich. Jupiter's immense gravity, radiation, and magnetic fields may alter the comet's coma or deflect its path slightly. NASA's Juno spacecraft, already orbiting Jupiter, might observe the flyby if its mission is extended, something Congresswoman Luna has publicly urged. Beyond Jupiter, the comet will fade from view, crossing the orbits of Saturn, Uranus, and Neptune over the next few years. Eventually, it will pass the heliopause, the boundary where the solar wind gives way to the interstellar medium and once again become a true interstellar object, wandering between stars for millions of years. We will never see it again. This December campaign is therefore both culmination and farewell. 3I Atlas carries matter formed long before our Sun existed. Its composition preserves the chemistry of a molecular cloud from an earlier era of the galaxy. Every spectrum and image adds a new clue to how planetary systems form and evolve elsewhere. There's a quiet poignancy in that finality. Unlike periodic comets, this one will not return. Once it leaves the solar system, no spacecraft or technology of our time can catch up. December is the high point of discovery and the start of the long goodbye. Even after it disappears, the data will keep it alive in research. Comet scientists analyzing coma structure, spectroscopists extracting molecular signatures, and dynamicists tracing its orbit backward to infer its origin. Though the uncertainties are large, tiny measurement errors multiply over interstellar timescales. Those calculations may point to a region of the Milky Way where 3I Atlas began its journey, perhaps 7 to 11 billion years ago. We may never know its exact home star, but even a rough trajectory tells us something profound. Interstellar comets are not rare. Statistical models suggest that at any given moment, one or more objects like 3I Atlas are quietly passing through our solar system. Too small, too dark, too faint to notice. Occasionally one of them awakens, its ice is warmed by the sun. It flares into light, revealing itself for a few brief months. Then it slips back into darkness, leaving behind a trail of data and wonder. 3I Atlas is simply the latest of these visitors, and perhaps the most carefully studied one yet. As December unfolds, astronomers around the world will watch, record, and share the moment. The comet follows the laws of physics that existed before Earth formed and will persist long after our species is gone. But for this brief time, we get to witness it, to measure, to learn, to look up. 3I Atlas will fade, the instruments will turn elsewhere, and the sky will return to silence. Yet for those who observed it, the memory will remain, a fragment of another world, crossing ours, reminding us that the universe moves with its own quiet rhythm, indifferent, immense, and magnificent. As those images accumulate, the comet transforms from a faint blur into data, lines of numbers, spectra, and light curves. Each one measures the behavior of matter older than the sun itself. What began as an act of personal curiosity now feeds a global archive. Across research centers, teams compare results, refine orbital parameters, and test whether the comet's chemical ratios match known patterns or suggest something alien in composition. In a way, 3I Atlas turns the night sky into a kind of mirror. Its presence reminds us that everything familiar, water, carbon, rock, air, was once drifting like this between the stars. Comets such as this may have carried the seeds of those elements into young planetary systems. Their collisions, gentle or violent, could have planted oceans and atmospheres. Observing one from another system is like watching the beginning of a story we already live inside. The more precisely we track it, the clearer that story becomes. 3I Atlas is not simply a visitor, it's a sample of the galactic medium, the recycled dust of exploded stars, reshaped into ice and stone, then released again to wander. Its hyperbolic path will eventually take it past Jupiter's orbit, then outward beyond Neptune, and finally into the cold between stars. Long after the telescopes fall silent, it will keep moving, unchanged except for the thin layer scorched away by the sun. For astronomers, the value of such an object goes beyond curiosity. Interstellar comets reveal the diversity of planetary chemistry across the Milky Way. Each one is a probe built by nature. No engines, no instruments, yet perfectly equipped to carry information about where it came from. They teach us how common our kind of system might be, and how many different ways the same raw ingredients can assemble worlds. When the last exposures of 3I Atlas are taken, and its light finally fades below the reach of even the largest telescopes, the data will remain, a time capsule of one brief intersection between two star systems. Somewhere in that record is a reminder that the solar system is not isolated, but part of a vast exchange. Ice, dust, and starlight travel freely here, crossing the darkness in both directions. Soon another such visitor will appear, maybe brighter, maybe dimmer, but carrying the same silent message. The galaxy is not empty. It is full of motion, memory, and material shared among countless suns. For a few weeks or months at a time, we get to witness one of those messengers, to trace its path, measure its light, and for an instant feel the quiet continuity between where we come from and where it's going. Even after 3I Atlas drifts beyond reach, its traces remain on Earth in terabytes of archived observations. Each spectrum, Each frame of telemetry becomes part of a shared repository, a reference for the next interstellar object. Researchers will spend years comparing its chemistry, refining orbital models, and reconstructing its path backward through time. By simulating its trajectory under the galaxy's gravitational field, they can estimate where it entered our region of space and how long it has been traveling. Most estimates suggest billions of years, a span so vast that the star that once hosted it may no longer exist. Understanding objects like 3I and Atlas isn't just an exercise in curiosity, it tests how well our theories of planet formation hold up beyond our own system. The data show that comets can survive interstellar travel intact, even after being bombarded by cosmic rays and dust grains for eons. That resilience implies that the basic components of life, complex carbon molecules, water ice, and silicates, can endure deep time and vast distance. If they can survive the cold between stars, they could also survive the birth of new systems, seeding planets with organic material before life begins. In that sense, interstellar comets act as couriers of chemistry. They move between worlds carrying evidence of the processes that shape them: condensation, irradiation, heating, and erosion. Each time one enters a new solar system, it reveals how the galaxy recycles its own material. By studying them, we glimpse the unbroken chain of matter, from dying stars to molecular clouds to new suns and worlds. The next steps will go beyond observation. Future missions, already on drawing boards at NASA and ESA, propose small spacecraft designed to intercept an interstellar object on short notice. Such a probe would need to launch within a year of detection, using high-efficiency engines to match the comet's enormous velocity. It might not land, but it could pass close enough to analyze gases, dust, and isotopes directly, the first true sampling of material from another star. Plans like these remain hypothetical, but 3I's Tug Atlas has given them urgency. Every visitor from beyond our system is a limited time event, and the next one might not wait decades. Meanwhile, back on Earth, the human part of this story continues quietly. Thousands of amateurs still share images, comparing how their data align with professional measurements. Online archives now hold hundreds of hours of exposures, from Chile to Finland to Japan, a global mosaic of a single fleeting object. The comet is gone, but the community it inspired persists. For many who watched it rise before dawn, that experience became a kind of calibration point, a reminder of scale, of motion, of how the universe operates beyond human rhythm. As the sun climbs higher each morning and 3I Atlas fades into the outer dark, the sky seems almost unchanged. Yet something subtle remains. The knowledge that the space between stars is not empty after all. It is full of travelers like this one, tiny, ancient, unannounced. They pass through silently, leaving behind only the faint light of their discovery and the data that will outlast us. One day another will come, brighter or nearer, and once again we will look up from our machines and remember that the universe is not something we visit. It's something we're inside. When the last confirmed observations of 3I Twins Atlas were logged, astronomers formally marked the end of its observing campaign. The data stream tapered off, but the analysis was only beginning. In a sense, this is when a comet's second life starts. Not in the sky, but in the calculations, conferences, and quiet work that follow. Inside the Minor Planet Center, analysts refine the comet's orbital parameters using every recorded position, each time-stamped to fractions of a second. Those tiny coordinates define the shape of its path through the solar system and hint at the gravitational nudges that shaped it. Once the trajectory was stable, dynamical modelers at JPL and ESA ran thousands of backward simulations, accounting for perturbations from Jupiter, Saturn, and even the galactic tide. The results suggested that 3I's Atlas had entered the solar system from a direction near the constellation Aquila, travelling on a hyperbolic orbit with an eccentricity slightly greater than 1. Its inbound velocity relative to the Sun was about 32 km/s, consistent with typical stellar motions through the local interstellar medium. No known star matched the exact vector, but the models traced its path back to a region of space that the Sun itself had passed through nearly 10 million years ago. That coincidence raised a quiet thought among researchers. Perhaps interstellar visitors are not so rare after all. Perhaps the solar system moves through streams of them regularly, invisible until chance brings one into view. Once the orbit was finalized, attention shifted to composition. Spectral data from JWST and ground-based observatories were compared in painstaking detail. The mixture of carbon dioxide, carbon monoxide, and water differed slightly from solar system norms, leaning toward higher CO2 ratios. Trace detections of ammonia, acetylene, and methanol appeared as faint absorption lines. Those molecular fingerprints may seem abstract, but together they describe the conditions in which the comet formed: pressure, temperature, and radiation intensity in the protoplanetary disk of another star. Several teams noted that the isotopic ratios of hydrogen and oxygen, while uncertain, hinted at heavier values than Earth's oceans. If confirmed, that would mean the water in 3I Anaard's Atlas condensed in a colder, more distant environment than ours, perhaps in the outer reaches of a system with a dimmer sun or older molecular cloud. Comparing such ratios across multiple interstellar comets could one day let scientists map chemical gradients across the galaxy, revealing how the raw materials for planets vary from region to region. The excitement spread beyond astronomy departments. Planetary scientists, chemists, and astrobiologists joined discussions about what interstellar comets might deliver if they ever collided with young worlds. Computer models showed that even a small impactor could release complex organics, contributing to a planet's prebiotic inventory. That idea isn't new. The panspermia hypothesis has floated for decades, but now, for the first time, there was direct evidence that solid bodies truly move between star systems. The barrier between here and out there suddenly looked thinner. The phenomenon also stirred debate about readiness. If another object like 3I Atlas were discovered tomorrow, how quickly could humanity respond? Current sky surveys such as Pan-STARRS and the upcoming Vera Rubin Observatory can detect faint moving objects. But interstellar comets travel fast and appear with little warning. By the time they're noticed, they're already on their way out. That realization pushed agencies to draft protocols for rapid response missions. Small spacecraft, pre-built and stored in orbit, could be launched within months to perform flybys or sample analyses. The idea is not science fiction. Engineering studies under NASA's Interstellar Probe concept show that compact ion engines could reach required speeds if given early notice. Behind the technical planning sites a philosophical shift. For centuries, comets were symbols, omens, then curiosities, then archives of solar system history. Now they are becoming tools for studying the galaxy itself. Each visitor expands the boundaries of comparative planetology. Just as meteorites once revealed the chemistry of the asteroid belt, interstellar comets could reveal the chemistry of distant suns. Media attention inevitably waned as the comet faded, but inside research circles, it left a subtle imprint. Funding proposals began referencing interstellar object readiness. Graduate students who had cut their teeth analyzing 3I, Little's Atlas spectra, designed new detection algorithms. Instrumentation teams tweaked filters and detectors to better isolate the faint signatures of CO+ and CN emissions at high velocities. The comet had become a benchmark, a test case for future encounters. A year later, papers summarizing its behavior appeared in Nature Astronomy and the Astrophysical Journal. The conclusions were modest but significant. 3A Shishint's Atlas, likely formed in a cold outer region of a planetary disk, underwent long exposure to cosmic radiation and remained chemically active even after billions of years in interstellar space. Its hyperbolic orbit confirmed that it was not bound to the Sun and would never return. Yet its stability suggested that countless others like it must exist. Fragments of planetary systems slowly dispersing through the galaxy. HT changes perspective. Instead of seeing our solar system as a closed bubble, scientists now picture it as part of a vast exchange network. Grains of dust, comets, and even microscopic organisms may drift between stars over cosmic timescales. The distances are immense, but time is generous. Given billions of years, even improbable journeys can succeed. For the public, the comet's legacy is simpler, but no less important. It restored a sense of wonder grounded in fact, not fantasy. No lights, no signals, no drama. Just a small body of ice and dust obeying physics perfectly, reminding us that the universe does not need embellishment to be extraordinary. Teachers used its story to explain orbital mechanics and spectroscopy. Artists used its path as metaphor. Students learned that discovery often begins with patience and ends with humility. As technology advances, the boundary between professional and amateur astronomy keeps fading. When the next interstellar object appears, it's likely that the first confirmation will come not from a government observatory, but from a network of automated backyard telescopes already scanning the sky each night. Data will flow instantly, shared openly, analysed collaboratively, a decentralised science born of shared curiosity. That too is part of 3I Glass Chi Atlas's influence. Years from now, when the comet is halfway to the heliopause, its faint light will still appear in historical databases as a brief streak, one more trace of the galaxy's endless motion. By then, the equipment used to capture it may already be obsolete, replaced by instruments capable of tracking smaller, faster, dimmer objects. But the principle will remain the same: to look outward, measure carefully, and let the evidence speak. Perhaps in some future century, a probe launched from Earth will overtake one of these wanderers. It might drift alongside long enough to photograph the untouched surface, to taste its gases, to read the isotopic script written before the sun was born. If that ever happens, scientists will look back to 3 Atlas, the comet that taught them what questions to ask and what instruments to build. For now, its journey continues, invisible to us, crossing the deep that separates stars. It carries no message, yet it delivers one all the same: that everything in the universe moves, mixes, and connects. The boundary between systems is only temporary, the space between them is a highway of matter and time. And every so often, when the geometry is right and the light is kind, we catch a glimpse of that passage, a reminder that we too are travellers in motion. As 3I, Atlas moves farther from the Sun, it enters a region where sunlight fades to a fraction of what reaches Earth. The solar wind weakens. Dust particles settle into slower streams. In that silence, the comet's activity dwindles until only its inert nucleus remains. What once glowed with vapor and light is now a dark frozen stone again, a tiny world carrying a record of its passage through our system. For astronomers, this phase is both an ending and a beginning. The comet itself is gone, but its data open new lines of inquiry. Thermal models that once relied on guesses can now be tested against observations. Spectroscopic catalogues grow richer, filling in missing wavelengths. Each correction, each recalibration improves the next generation of predictions. The science is cumulative, built one faint trace at a time. Even outside the scientific community, traces of 3I Atlas remain. Documentaries and museum exhibits use its images to explain the difference between bound and unbound orbits, between local and interstellar matter. In classrooms, teachers show how a single observation links mathematics to physical reality, how an object's motion across a CCD sensor can reveal velocity, distance, and origin. The comet has become a teaching tool, proof that discovery is not confined to distant epochs or deep space missions, but can still happen through patience and careful measurement. At the same time, the event has changed how we think about space itself. Before the discovery of interstellar comets, many pictured the solar system as a bubble drifting in isolation. Now, that image feels incomplete. We know there is traffic in the darkness, fragments of other worlds passing through ours, and perhaps pieces of our own system escaping outward. A few billion years from now, the Sun's debris will cross the same distances, carrying chemical signatures of Earth into unknown skies. 3I? Atlas simply gave us a glimpse of that exchange happening in real time. That realization has practical consequences. Space agencies have begun to treat interstellar encounters as a predictable category of event rather than an anomaly. The Vera Rubin Observatory, soon to begin full operations in Chile, will survey the entire visible sky every few nights. Its automated detection algorithms can flag fast-moving objects with unusual trajectories, the kind that hint at interstellar origin. Where past discoveries depended on luck, future ones may become routine. Parallel efforts aim to prepare for those discoveries. Mission planners at NASA, ESA, and JAXA have discussed ready-to-launch interceptors, small spacecraft stored in orbit, fueled and waiting for a target. Once an interstellar object is found, a single command could send one of these probes onto a rapid transfer path. The first prototypes would not attempt landing, but could pass within tens of thousands of kilometers, sampling dust and gas with onboard spectrometers. If successful, that would mark a new era, the first direct study of material formed under another star. Funding such ambitions requires political will, but the case is persuasive. Unlike deep space flagship missions that take decades, an interstellar object probe is compact, relatively inexpensive, and scientifically rich. A single close flyby could tell us more about galactic chemistry than years of remote observation. Policymakers increasingly understand that chance favors readiness, and that readiness in astronomy is a form of foresight. The comet's cultural resonance continues in quieter ways. Artists paint its arc across stylized star fields. Composers fold its orbital data into digital soundscapes. Poets use its single-visit trajectory as a metaphor for impermanence. These interpretations matter because they help translate scale. They turn units like astronomical distances or magnitudes into feelings humans can hold. Science provides precision. Art supplies perspective. Both are needed to make sense of something that travels billions of kilometers, yet lasts in view for only a few months. Among scientists, the discussions are more technical, but no less philosophical. One recurring question is whether 3I Atlas and its predecessors, 1I Oumuamua and 2I Borisov, represent a continuum of interstellar objects or distinct categories. Oumuamua was dry, asteroid-like, and unusually shaped. Borisov was a typical comet rich in volatile ices. Atlas lies somewhere between. If these three are representative, then the Milky Way may contain a full spectrum of interstellar debris, rocky, icy, and mixed. Future detections will fill in the gaps and, over time, yield a statistical view of how other planetary systems shed material. Another avenue of research looks inward rather than outward. If interstellar objects can enter our system, could any have done so unnoticed in the past, or even struck Earth? Geochemists are re-examining micrometeorite collections for isotopic anomalies that might betray non-solar origins. A few candidates show promise, with unusual nickel and chromium ratios inconsistent with known meteorites. If confirmed, that would mean fragments of other star systems have literally landed here, waiting in our sediments to be identified. The thought reshapes planetary science. Instead of viewing Earth as an isolated record, we begin to see it as an archive that includes interstellar pages. Our planet is not just a witness to local history, but a collector of galactic debris. Meanwhile, technology keeps pushing boundaries. New detectors sensitive to ultraviolet and sub-millimeter wavelengths allow even faint comets to be studied across their full thermal range. Artificial intelligence algorithms now assist with real-time detection, filtering millions of images nightly. If the pattern holds, the next interstellar visitor may be recognized within days of arrival, early enough to observe its inbound leg, something never achieved before. The broader implication is that astronomy itself is becoming faster, more responsive, more connected. Where once data took years to analyze, researchers now collaborate in near real time. A discovery in Chile can trigger a response from Hawaii within hours. That global web of instruments functions almost like a single observatory spread across the planet. 3I Atlas accelerated this transformation by giving the community a common, time-sensitive goal. For the public, what lingers is the idea that the universe is accessible, not in a touristic sense, but intellectually, that with the right tools and attention, anyone can participate in discovery. Images of the comet taken through modest telescopes proved indistinguishable, in essence, from those captured by professional instruments. That democratic truth may be the most lasting legacy of all. As the years pass, 3I Atlas will drift into the outer dark. It will cross the orbit of Neptune, then Pluto's distant path, until even the Sun becomes a bright star behind it. Radiation and micrometeorite impacts will slowly erode its surface, exposing layers untouched since its formation. In 100,000 years, it will pass through the outer edge of the heliosphere. Beyond that lies true interstellar space, a vacuum so thin that a single atom may drift for meters before striking another. There, the comet will continue on its inert course, another seed cast into the galactic field. Back on Earth, the story becomes memory, then history. But within that history lies continuity. Each observation, each data point, forms a bridge to what comes next. Children who looked through telescopes in 2025 may one day analyze data from an interstellar probe. Their work will rest on the foundation built by those who watched a faint blur rise before dawn and decided it was worth understanding. If the past century was about reaching planets, the next may be about reaching between stars, not through grand voyages, but through attention. Each interstellar object that enters our skies offers a new piece of evidence, a small truth about the greater system we inhabit. And each one reminds us of an older fact. Discovery is less about distance than about awareness. The cosmos does not hide. It waits to be noticed. By the late 2030s, a quiet revolution begins to take shape in astronomy. The lessons learned from 3i, Atlas, guide the design of a new generation of instruments. Automated sky surveys, once limited by data volume, now rely on AI-assisted recognition systems capable of identifying transient objects within minutes of detection. Machine learning algorithms, trained on decades of comet images, can distinguish a faint interstellar trajectory from background noise almost instantly. Where once discoveries depended on human luck and patience, now they emerge from pattern recognition at planetary scale. Dozens of observatories feed their data into shared neural networks, creating a living, evolving map of everything moving across the night sky. Every unusual orbit, every strange light curve is flagged and verified. By then, the term interstellar object no longer evokes surprise. They have become expected guests, unpredictable in timing, inevitable in occurrence. In this new landscape, the distinction between observer and participant blurs. Astronomers, programmers, and citizen scientists all contribute data to the same open repositories. A teacher in Chile can upload a student's telescope image to the same archive used by the European Southern Observatory. An AI filters it, cross-checks coordinates, and within minutes updates a global dashboard of small body motion. Discovery has become collective, a conversation between humans and machines across continents. That change echoes the spirit of 3i Chuon Atlas. The comet was never just a scientific event, it was a rehearsal for cooperation. It showed how quickly expertise and curiosity can align when the sky offers something worth chasing. When the next object, 4i, Daedalus as it was later named, appeared in 2034, the response was instantaneous. Within 12 hours of its first detection, telescopes on 6 continents and 2 spacecraft were already tracking it. That speed was possible only because of the frameworks built in Atlas's wake. Scientific capability, however, is only one part of the story. The deeper shift lies in how humanity sees itself against the cosmic background. For centuries, we have treated space as a frontier, a place to reach, to conquer, to map. The discovery of interstellar objects subtly undermines that view. It reminds us that the frontier is not out there, it passes through us continuously. We live within the flow of the galaxy, not outside it. Our solar system is just one eddy in a vast, circulating stream of matter and motion. This realization has quiet philosophical weight. If the dust that formed Earth came from many stellar sources, then the atoms in our oceans and bodies are already interstellar. When we study comets like 3I Atlas, we're not looking outward so much as inward, tracing the larger network we've always been part of. It's a kind of cosmic ecology. Stars give birth, planets evolve, debris escapes, and over immense time it all blends back together. We are participants in that process, not spectators. Scientists, though typically cautious about poetry, acknowledge this interconnection in their own way. Research papers now include sections on galactic context, situating each finding within the broader chemical flow of the Milky Way. What once seemed esoteric, stellar nucleosynthesis, molecular clouds, cosmic rays, now ties directly to everyday evidence. A sample of comet dust on a lab bench becomes a trace of another star's life cycle. The distinction between astronomy and geology begins to dissolve. The impact extends into education. Universities design interdisciplinary programs combining planetary science, astrochemistry, and data engineering, training students to navigate both cosmic scales and algorithmic ones. Fieldwork might mean a desert observatory, a data cluster, or a clean room preparing sensors for a near-sun flyby. The frontier has moved from geography to comprehension, learning to read complexity faster, with greater care. Meanwhile, a quiet competition develops between space agencies and private companies. Each wants to be first to intercept an interstellar object. Several prototypes are already under construction. Lightweight nuclear-powered probes designed to launch on short notice and accelerate continuously using ion or fusion-augmented drives. The most ambitious, the Interstellar Interceptor Mission, IIM, coordinates engineers from multiple countries. Its goal, to reach the next visitor before it leaves the inner solar system, analyze its surface with laser spectrometry, and transmit data before the signal delay grows too long. Public enthusiasm returns in waves. Live feeds of sky surveys replace news cycles for a day whenever a new candidate appears. Children learn to interpret orbital plots as easily as weather charts. The language of discovery becomes ordinary vocabulary: perihelion, albedo, hyperbolic excess. This democratization of knowledge, subtle and cumulative, owes much to that first shared experience of Atlas. It turned the abstract idea of interstellar into something real enough to point at, measure, and remember. Beyond the technical, new moral questions emerge. If matter constantly crosses from one system to another, what responsibility do we have toward the material we release? Our satellites, probes, and waste. Could fragments of human technology someday drift through another star system as their first evidence of us? Scientists begin drafting ethical guidelines for outbound debris. Radio silence after a certain distance. Data signatures identifying origin. Respect for potential biospheres, even if hypothetical. It's not legislation yet, but it's the early architecture of what might one day be called interstellar environmentalism. Culturally, the idea reshapes how we tell stories about ourselves. In literature and film, the motif of contact evolves. Instead of messages from intelligent beings, narratives center on contact with the non-living, dust, ice, and light, that carry memory without intention. Audiences start to grasp that communication doesn't always mean conversation. Sometimes it means recognition. That shift from expectation to awareness mirrors what science itself has learned. The universe speaks, but not in words. Meanwhile, back in the scientific archives, the data from 3I Databasen Atlas remain active. Reprocessed with better calibration, they continue yielding insights decades later. Subtle variations in its coma brightness reveal oscillations that may hint at rotation or internal structure. Even as new comets are found, Atlas serves as the baseline for comparison, the yardstick by which each newcomer is measured. Its once temporary fame has turned into permanent reference. The larger picture that emerges is one of continuity. Discovery no longer ends when the light fades. It folds into ongoing analysis. Each object adds a pixel to the galactic mosaic, a small point of evidence that over centuries will reveal the Milky Way's deeper architecture. Scientists may never visit other stars directly, but by cataloguing their debris, they effectively map the invisible corridors connecting them. In this sense, interstellar research becomes a long conversation across time. Each comet is a line in that dialogue, each detection a response. What we learn from one generation's data guides the next's instruments, and so on, until the thread of inquiry itself becomes the legacy. And yet, despite all the technology and precision, the essence remains simple. A person stands beneath a cold sky, looks up and wonders what moves there. That impulse, older than any telescope, survives untouched. It's what links the early skywatchers who named constellations to the scientists who now pass spectra. 3. Atlas only reminded us of the continuity, that curiosity, scaled and amplified, is still the engine of every discovery. In the centuries ahead, when the comet's dust has dispersed and the sun has aged a little further along its main sequence life, future astronomers will still cite the data from 2025. They'll trace our instruments' limitations, our approximations, our cautious language, and perhaps smile at how much we didn't yet know. But they'll also recognize something enduring, the patience to record, to compare, to understand. That patience is the real inheritance. The galaxy will keep sending its messengers. We'll keep receiving them one after another until the pattern becomes routine again, as familiar as sunrise, and each time we measure one, we'll be measuring ourselves, our reach, our restraint, our evolving sense of belonging in a universe that was never distant to begin with.